The next important concept in this section is that of inverse functions. The example here to give us some context is the conversion between Celsius and Fahrenheit in temperature. So the United States and just a few other countries use Fahrenheit scale for measuring temperature. Most of the countries use Celsius to measure temperature. We have an example. If an American visiting France hears the local temperature will reach a high of 20 degrees, it would be helpful to be able to convert that 20 degrees Celsius into Fahrenheit so that the American has a better idea of what that temperature is for what they're used to. Similarly, if we look at, for example, someone from Canada coming to America, they may want to take the Fahrenheit and translate it to Celsius so that it makes more sense for them. Now, I know there are apps on your phone that will do this immediately, and a lot of temperatures are given in both scales for the very reason of helping everyone with that knowledge. But let's roll with this. So there is a function that converts Celsius to Fahrenheit. We're going to call that function g. So it takes a Celsius temperature and it turns it into a Fahrenheit temperature. But similarly, if we want to go the other way, we want to take a Fahrenheit temperature and turn it back into Celsius. We call this the inverse of g because it's doing the inverse of what g does. G takes Celsius, turns it into Fahrenheit. Inverse of g is taking Fahrenheit and turning it back into Celsius. So, some observations that we can make about the inverse function. G inverse takes outputs and turns them into inputs. So G inverse sends outputs of G to inputs of G. The example here, G of 0 is 32. So 32 degrees Fahrenheit is equivalent to 0 degrees Celsius. It's the freezing temperature of water. The inverse function takes the Fahrenheit temperature back to Celsius. And the second observation, the inverse function undoes what the original function did. That's why they're called inverse functions. It's very similar to the idea of adding 5 and subtracting 5 cancel each other out, and you're left with whatever you started. That's the same thing here with an inverse function. Also with multiplication and division, multiplying by 3 and dividing by 3, we end up with what we started. With an inverse function, though, instead of just these single operations, addition, subtraction, multiplication, division, we can combine these operations into a function expression, and if the function expression is the right kind of function expression, which we'll talk about, then we can find that inverse function that will do the opposite, that will do the complementary operations in the opposite order so that it all works out and we end up with what we started. Okay, if a function has an inverse, then f of a equals b and f inverse of b equals a are equivalent statements. If f sends a to b, then f inverse sends b to a, and vice versa. If f inverse sends b to a, then f sends a to b. So let's look at a definition. Before I talk about the definition, I do want to address the small elephant that has walked into the room without me talking about it. This notation right here is notation. It's a name. It does not mean 1 over f. Even though traditionally a -1 exponent would mean take the reciprocal, that is not the case for a function name. It's just a name, it's just a notation. So f and f inverse, the inverse noted by this little exponent of -1. Again, notation, not an operation. It's a name. So if I have inverse functions, then the following are true. The domain of f is the range of the inverse, and the range of f is the domain of the inverse. So if we have two sets here, and f takes one set and maps it to the other, the inverse function takes the second set and maps it back to the first set. And that's what we mean by domain of f is the range of f inverse. This would be the domain of f, but the range of f inverse. And this would be the range of f, but the domain of f inverse. If I have a point A, B on the graph of f, then the point BA will be on the inverse graph. The two graphs are symmetric over the line y equals x. We'll take a look at that a little bit later. And pulling in this idea of compositions, if I compose a function with its inverse, I end up with what I started with, x. One thing that I didn't put in this set of notes that I would like to talk about, a function f has an inverse if f is 1, 2, 1. So recall the definition of a function. A function is a correspondence between two sets such that every x value has exactly one y value. That's a function definition. And we could identify functions by the vertical line test. To determine if a function has an inverse, every y value has to have exactly one x value corresponding to it. So notice the roles are reversed in our variables. And we have a horizontal line test that would help us with this. So some examples really quickly. If I have the function, just a simple cubic function, so f of x equals x cubed. This is a function. I draw vertical lines, I hit that graph in only one place. Each vertical line hits it at most one time. This graph is also 1 to 1 because every y value has exactly one x value. So drawing horizontal lines this time, horizontal lines hit the graph in at most one place. So f of x equals x cubed has an inverse function. To contrast, let's just take the very simple, one of our favorites, x squared. This is a function, again, vertical lines hitting that graph in only one place, or at most one place. But now if I draw horizontal lines, I can get a horizontal line to hit it one place, that's on the x-axis, but notice these other horizontal lines are hitting it twice. So 2 hits for the same line. X squared does not have an inverse function as it is. If you're headed on to trigonometry, you'll talk about how instead of looking at this whole function, we only look at half of the function, and we can consider just that half of the function. Now we have a one-to-one function, and we can talk about an inverse, but we have to cut a piece of the function off to get that to happen. That's more advanced than we want to do. I just want you to be aware that we can restrict our domain. So we shrink our domain set to allow for inverses of what normally wouldn't have inverses. So again, leaving that for future semesters in college algebra and trig, going back to what we're talking about with our inverse functions, we have this horizontal line test that we can use to determine if a function has an inverse or not.